Welcome to the fourth lecture in Applied Math. The topics that we will explore in this lecture include symmetric groups, dihedral groups, and an introduction to point groups with an application to chemistry.
Okay, so we'll start with the exercise from the previous lecture. Let X be a set, and let T of X be the set of all transformations of the set X. Then the set of all transformations of X together with function composition is a group. So proof: let F and G be two transformations in the set of all transformations of X. Then the function F is a map from the set X into the set X, and G is a map from the set X into the set X, and both F and G are bijections. And so the composition F of G is a map from the set X into the set X and is also a bijection. Since the composition of two bijective functions is a bijection, and hence the composition is also a transformation of X. Now, we have already demonstrated that function composition is associative. Now there exists the identity map, which is a transformation on the or of the set X that leaves all the elements unchanged, such that for every transformation in the set of all transformations of X, we have that the composition of the identity with F of the element X is the identity of f of x, the element f of x, which is the element f of x for every element x in the set X. And the composition f of the identity of an element x is f of the element, the identity map of the element x, which is f of x for every element x in the set X. That is, the composition of the identity with the function f is the same as the composition of f with the identity, which is the element f, or the map f. Now, for every transformation in the set of all transformations, the inverse of that transformation is a map from the set X into the set X and is also a bijection, and hence the inverse of any element or any transformation in the set of transformations of X is once again a transformation of X. And thus the set of all transformations of the set X is a group under function composition. Okay, so new definition. Let G be a group under some binary operation, and let H be a subset of G, then H is a subgroup of G, and this is denoted this way using the same symbol for less than or equal to, but in the context of group theory this is read H is a subgroup of G if and only if H is itself a group under the same operation as in the group G, and we refer to this as the induced operation from G. Now if H is a proper subset of G and H is a subgroup of G, we write H less than G, and we call H a proper subgroup of the group G. Okay, so we will prove a lemma. Let H be a subset of a group G, then H is a subgroup of G if and only if the following conditions hold. The first condition is that H is closed under the same operation as in G. The second condition is that the identity element is in the set H. And the third condition is that for every element in the set H, the inverse of that element is also in the set H. So proof. Suppose that H is a subgroup of G, then H is itself a group under the same operation as in the group G. And so conditions 1 through 3 hold by definition. Conversely, suppose that H is a subset of G such that conditions 1 through 3 hold. Then, to prove that H is a group, it only remains to show that the operation is associative over the set H. So let A, B, and C be any three elements in the set H. Then, as H is a subset of G, these elements A, B, and C are in the set G. And since G is a group, the operation is associative, and hence H is a group under the same operation as in G, where H is a subset of G, and thus H is a subgroup of G. Okay, so we will now use this lemma to prove a theorem. So let H be a non-empty subset of a group G. Then H is a subgroup of G if and only if for every two elements A and B in the set H, the operation of the element A and the inverse of B is also in the set H. So proof. Suppose that H is a subgroup of G, then H is itself a group under the same operation as in the set G. And so for every element in the set H, the inverse of that element is also in the set H. And hence, for every two elements, A and B, in the set H, the operation of the element A and the inverse of B is in the set H, as H is closed under the operation so conversely, suppose that H is a non-empty subset of G such that for every two elements A and B in the set H, the operation of the element A with the inverse of B is in the set H. Then, as H is non-empty, there exists at least one element A in the set H, and so the operation of A with the inverse of A, which is the identity, is in the set H. Now since the identity and an element A is in the set H, the operation of the identity with the inverse of A, which is the inverse of A, is in H. And so for every two elements A and B in the set H, we have that the element A and the inverse of B is in the set H. And hence the operation of the element A with the inverse of B, which is the operation of A and B, is in the set H. And so H is a subset of G that is closed under the same operation as in G that contains the identity element, and for every element in the set, the inverse is also in the set. And so by the previous lemma, H is a subgroup of G. So as an exercise, let G be a group and let A be an element in the set G. Prove that the set of all integer multiples of that element A is a cyclic subgroup of the group G. Okay, so new definition. Again, let X be a set, and let T of X be the set of all transformations of the set X. Then any subgroup which we'll call G of the group of all transformations of X under function composition is called a transformation group of the set X if, in addition, the underlying set X is finite, then any subgroup G is called a permutation group. Of the set X. Now notice that the group of all transformations of X is not abelian, since it is not necessarily true that for every two transformations F and G, that the composition F of G is the same as G of F. And we saw a counterexample in the previous lecture. Okay, so new definition. The group of all permutations of the set of consecutive integers from 1 to n is called the symmetric group on n letters and is denoted S sub n. Now let pi be a permutation in the set of all permutations on the consecutive integers from 1 to n. Then the element is represented this way. And this is a direct representation of the bijective map, where the integer 1 is mapped onto the integer a sub 1. The integer 2 is mapped onto the integer a sub 2, and so on, so that in general the integer n is mapped onto the integer a sub n.